All right, everybody, welcome to the start of chapter 3. In this chapter, we're going to be talking about stoichiometry. Stoichiometry is the quantitative relationship between species in a chemical reaction or species within a molecule. It's quantitative relationships. So if you think you have a chemical reaction and you need uh, 6 oxygen molecules two to eventually produce 2 carbon dioxide molecules. That's 6 to 2. That's a stoichiometric relationship. In carbon dioxide, CO2, you have 1 carbon to 2 oxygens. That's stoichiometry. So it's quantitative relationships. So let's start with the concept of atomic masses. So when you look at the periodic table, we've been looking at this so far and pulling out the atomic number. So for example, for nitrogen, it's 7. And so that'd be 7 protons in the nitrogen nucleus, 8 protons in the oxygen nucleus, 2 for helium. But we also get other important information from the periodic table. We get quite a bit. But the next one we're going to be looking at is the mass number from the periodic table. So the periodic table will tell us of the mass of an atom of an element. So as you see, nitrogen is about 14.007 U or AMU. U and AMU are used, you can use them interchangeably. They mean the same thing. They're atomic mass units. Oxygen is 15.9994, 15.999 U. When you're doing your assignments and whatnot, we usually approximate oxygen to about 16. Helium, you see, is about 4.0026 U. So this tells you the mass in atomic mass units of an atom of these elements. And you can see here the relationship of the atomic mass unit to grams. That can be very helpful when you're doing calculations for conversion. The mass of an atom gives you an insight into the nucleus of that atom. So I don't know, let's look at oxygen for a second. So in oxygen, you remember when we were working in last chapter, we were talking about isotopes, and we know that when you take the number of protons plus the number of neutrons, you get the mass. So for oxygen, we're going to say that's about 16.0. Okay, well, my neutrons are going to be about 16.0 minus the number of protons. Oxygen's number of protons is 8 from its atomic number. And so the oxygen atom should have about 8 neutrons in its nucleus. There will be different isotopes, but still, the mass number on the periodic table can give you an insight into the nucleus of these various elements. But these mass numbers are fractional, meaning they're a decimal point number. They're not a nice round whole number. And so what happens in nature is all of these elements exist in various isotopes. And anytime you find a sample of an element, let's say you find iron ore. Within that iron ore, you're going to have a mixture of all of the naturally occurring isotopes of iron. You don't just have a single isotope. And that happens for every element. Oxygen, you're going to have, see here, you have 3 naturally occurring isotopes, oxygen 16, oxygen 17, oxygen 18. And then you have their relative percent abundances in nature. So oxygen 16 is, of course, the most abundant at 99.7%. And oxygen 17 and 18 have very, very low percentages, but they're still there in a specific amount. And so these fractional masses that you see on the periodic table are an average mass of all of the different isotopes that are present in nature. And we can actually calculate what the mass number of an element should be based off the isotope masses and their percent abundances. So if we want to calculate the mass number of an element based on its the abundances of its relative isotopes, we have this equation here. So your M sub A, that's going to be your average atomic mass. Your A sub I is going to be the percent abundance or the fractional abundance for isotope I. And then M sub I is the mass of isotope I. And so it just depends on how many isotopes you have. So you're going to multiply the percent abundance times the mass of the isotope plus the percent abundance times the mass of the next isotope plus the percent abundance times the mass of the next isotope, so on and so forth. So for example, if we were to use this to try to figure out the average mass for oxygen, you notice here that we have these three isotopes. So what we would do is start with a theorem. And look at this. So if you compare to up here, you notice that the sum went from 1 to n. Well, n is just the number of isotopes you have. So for oxygen, since you see we have three naturally occurring isotopes, this sum goes from 1 to 3. 3 being the maximum number of isotopes of oxygen. And what this would turn into then is we would have percent abundance 1 times the mass of isotope 1 plus the percent abundance 2 times the mass of isotope 2 plus the percent abundance 3 times the mass of isotope 3. And that would give us the average mass of oxygen. Now, I want you to see how these numbers actually go into the equation, because here, like for example, we have 99.757%. But that is not what we put into the equation. What we put into the equation is the decimal point representation of a percentage. So what you would end up doing is taking all three of these percentages and dividing them by 100 to get their decimal point representations. So what you would actually get here for oxygen, so your first percentage would be 0.9976 to represent the 99.7% times the mass of oxygen 16 plus 0.205 divided by 100 is going to be 0.00205 times the mass of oxygen 17 plus, then your last one, 0.038 divided by 100, 0.00038 times the mass of oxygen 18. So that's how you actually put the percentages into this equation to figure out the average atomic mass of your element. And again, your average atomic mass is what you see here on the periodic table. So it's actually worked through a problem. So here we have the element gallium, and it has two isotopes having masses 68.95 atomic units and 70.95 atomic units. If the abundance of the lighter isotope is 60.16%, what is the average atomic mass of gallium? It may seem like you don't have enough information, but what we say is, well, the problem is asking for the average atomic mass. And what do we know? We know that abundance 1 so it's 60.16% or 0.6016, which is the number we would need for our calculation. The mass of isotope 1, and it said that this 60.16 is for the lighter isotope. So that means this is going to be our 68.95 atomic units. But then we also know that our mass of isotope 2 is 70.95 atomic units. Okay, so now we know what we're being asked. We know what we have. How do we figure out that second percent abundance? So here's the key. All of your naturally occurring isotopes, their percent abundances have to add to 100%. So here I have two isotopes for gallium. I have a percentage for one. The percentage of the first gallium isotope plus the percentage of the second gallium isotope has to equal 100. So that means to find the second abundance, we could do this two ways. We could do 100 minus 60.16, and we would get about 39.84% or 0.3984. You can do it that way, or you could realize that 100 is actually is 1. When you're using the decimal notations for percentages, 100 will be 1 minus what? 0.6016. And again, we get 0.3984 as our second abundance. So that one there, 1 or 100%, if you're taking any physics classes and you see the textbooks say unity, that's what unity is. It's 100%. It's 1. So when it says everything tends to unity, that means everything is going to be related to 1. And so that can also help you figure out problems based off terminology. So however you do it, you get your your second abundance. Now, we're going to go to the theorem we need to fill out. There's only two isotopes of gallium, so the sum is from 1 to 2. Abundance times mass. And this is going to be abundance 1 times mass 1 plus abundance 2 times mass 2. Now for us, so abundance 1 is 0.6016. Mass 1 is 68.95 U plus abundance 2, there's 0.3984. And our second mass is 70.95 U. And when you multiply and add this all up, your average atomic mass for gallium is going to be 69.75 U. You can check yourself with these because you can compare your average your average masses to the periodic table. So let's look at this in a slightly different way. So bromine exists naturally as a mixture of bromine 79, and bromine 79 has a mass of 78.95 U, and bromine 81, which has a mass of 80.95 U. What is the approximate relative abundance of each bromine isotope in nature? Well, we have the masses. We don't have either of the abundances. But what we can do is get the average mass of bromine from the periodic table. So the first, what we're being asked for here. So the abundance of bromine 79 is what? The abundance of bromine 81 is what? That's what we're trying to figure out. So what do I know? The mass of bromine 79 is going to be 78.95 U. The mass of bromine 81 going to be 80.95 U. And if I look at the periodic table, I'll see that the average mass of bromine is 79.90 U. All right, now I have to ask myself, how can I set up an equation with these abundances? Well, remember, both isotopes have to add up to 100%. They have to add up to 1. So what I'm going to do is I'm going to say my abundance of bromine 79 is going to be X. I don't know what it is. And my abundance of bromine 81 is 1 minus X, because the two of them together have to equal X. If I find the abundance of 79, then 81 just has to be 100 minus whatever 79's abundance is. So these are my two abundances that I can put into my formula. I'm going to start here. This is going to give me abundance 1 times mass 1 plus abundance 2 times mass 2. Well, we can even take this a step further and call this the abundance of bromine 79 times the mass of bromine 79 plus the abundance of bromine 81 times the mass of bromine 81. All right, now I'm going to start plugging in. Let's see, that's going to be, so the abundance of 79 is X. The mass of 79 is 78.95 U. The abundance of 81, 1.0 minus X. The mass of 81 is 80.95 U. But you notice here how this all equals the average mass of bromine. So what I'm going to do is I'm going to plug in the 79.90 U. And so now I just solve for X. Okay. Well, the first thing I'm going to do is I'm just going to flip this equation because I like to have X on the left side. Let's see. So you can already see that this is going to be 78.95X plus 1.00 minus X, 80.95 equals 79.90. Now I'm going to multiply the 80.95 through. That's going to give me 78.95X plus 80.95 minus 80.95X equals 79.90. Let's see. I'm going to subtract the 80.95 from both sides, and then I'm going to combine my terms with X. So 78.95 minus 80.95, that's going to be a negative 2.0x. And then my 79.9 minus 80.95 is going to be a negative 1.05. The two negative signs is going to make everything positive, and X is going to be 0.525. Now, remember that your abundance of bromine 79 is X. So now you've solved for that. Your abundance of 79, 0.525. Multiply that by 100, and you get 52.5 All right. So then the abundance of bromine 81, that's going to be 1.0 minus x minus 0.525. That's going to equal 0.475. So the abundance of bromine 81 is going to be 47.5%. So these aren't too bad to work with. Just make sure you practice, and you will get some practice on your next assignment. Okay, so our next topic is the mole. I would really make sure you're wrapping your head around this, the information for these next few sections, just like you really need to be doing with naming compounds, because this is going to be quite important. So the main definition of a mole is in Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd inverse moles. And so if you've never seen a unit like this, if you've never seen a negative exponent, what that is the negative exponent means it's that unit is in the denominator. So here you see inverse moles just becomes 1 over moles. If I had x to the negative 3, that's going to be 1 over x cubed. X to the negative 6 is 1 over x to the 6, so on and so forth. That's what the negative exponent means. You're going to want to make sure you know how to use Avogadro's number to solve problems. So remember we talked about when you're looking at conversion factors, the number always goes with the unit in the top. Okay, so here's how Avogadro's number works. It's 6.022 times 10 to the 23rd something per mole. Okay, that's what the moles to the negative 1 means. So when you're using it, it could be 6.022 times 10 to the 23rd molecules per mole of molecules. 6.022 times 10 to the 23rd atoms per moles of atoms. It could be 6.022 times 10 to the 23rd protons per mole of protons, and so on and so forth. That's how it works. It's Avogadro's number of something per mole of that thing. This is a very widely used conversion factor in chemistry, so make sure you're getting used to this. And then we move on to what's called molar mass. Now, so far we've been using the masses in the periodic table in terms of atomic mass units. But now we're going to switch to the unit that's going to be more common, the one you'll use most of the time throughout chemistry, which is the molar mass. So if you look here for calcium, you see you have 40.078. Well, you know that that's 40.078 atomic mass units. However, it's the same number, 40.0, so 40.08 grams per mole. And those are the units for molar mass, grams per mole. And so again, if you think about it, this would be 40.08 grams per mole for calcium. So the mass number on the periodic table it's the same number for either atomic mass units, which is the weight, which is the mass of, and weight and mass are different. You'll learn that in physics, but the mass, atomic mass units are the mass of an atom, whereas grams per mole is the mass in grams of 1 mole of atoms of that element. And we can use the molar masses from the periodic table to calculate the molar masses of molecules. Molar masses of molecules is something you're really going to need when you're solving chemical problems. So let's take a look at what we have here. So this first one, I hope you can name it. You notice you have a polyatomic ion and a magnesium ion. This is magnesium sulfate. So I look at the periodic table, and magnesium is 24.31 grams per mole. And I put this on here for you to look at. So you see the mass number there. This will be more visible. 24.31 grams per mole. Sulfur, going to have a mass number of 32.07 grams per mole. And oxygen, now remember we said oxygen instead of 15.999, you're going to use, you can round to 16.00 grams per mole. So that's what we'll use. I put this on here. Some of these aren't the easiest to read, but if you use a periodic table, uh, if you look up periodic table on Google, there's one from a website. PubChem, that is one of the best you can use to study with. Also, it's the one I use when working through your assignments. So if you use the one from PubChem, you'll have the exact same numbers I'm using. Okay, so I look at the periodic table, and of course, sulfur is going to be 32.07 grams per mole. And oxygen, we're going to round it to 16 grams per mole. And so now the way we get the molar mass of this molecule is we need to add everything together. So we're going to have 1 magnesium plus 1 sulfur plus 4 oxygens. And notice here it's 4 oxygens because of that subscript. So that's going to equal so your magnesium is 24.31. Your 1 sulfur is 32.07 plus 4 times 16.00. And your molar mass of magnesium sulfate is 120.38 grams per mole. All right, let's look at the next molecule. Well, here, you see you have 2 polyatomic ions. NH4 is ammonium. PO4 is phosphate, so this is ammonium phosphate. And make sure you understand that this subscript 3 here is because each ammonium is +1. Phosphate's a 3 minus. So I need 3 of the ammoniums to neutralize the phosphate. But that subscript's also going to play a role. So let's go through and first figure out. Look at the periodic table. Nitrogen is 14.01 grams per mole. Hydrogen 1.01 grams per mole. Phosphorus 30.97 grams per mole. And oxygen are 16 grams per mole. Now when we're adding this together, so this subscript 3 is going to come into the nitrogen, going to come into the 4. So we are going to have 3 nitrogens plus 12 hydrogens, because 4 times 3 is 12. One phosphorus plus 4 oxygens. And that's going to be 3 14.01 plus 12, 1.01. Plus the 30.97 for phosphorus plus 4 times 16. So the molar mass of ammonium phosphate is 149.12 grams per mole. All right. What's after this? Okay. So our next compound, again, we have another ionic compound. You see the sodium ion. You see the acetate ion. All right. So I'm going to say sodium is 22.99 grams per mole from the periodic table. Carbon, 12.01 grams per mole. Hydrogen, 1.01 grams per mole. And of course, oxygen is again 16 grams per mole. And then what do we have to add together? Well, we have to add the sodium, 2 carbons, 2 plus 3 hydrogens plus 2 oxygens. And so that's, let's see, no, hang on. Oh yeah, so 22.99 for the sodium. Let's see, 2 carbons, 12.01. 3 hydrogens, 1.01, and 2 oxygens, 2 times 16. So your sodium acetate is going to be 82.04 grams per mole. And so work through, okay, first let's name this next one. I hope well, eventually you'll get to the point where you recognize you have a polyatomic ion and the potassium ion. And so potassium, remember it's column 1 of the periodic table, so it's a +1. The cyanide polyatomic ion is a -1, so it's just KCN, and this is potassium cyanide. So I want you to go through and use the periodic table, get the molar masses, add this up. Your potassium cyanide should come out to be 65.12 grams per mole. So a pretty straightforward process. You just got to make sure you do it, get everything you need, add it all together in the proper amounts. Your amounts are based off the subscripts. I think the hardest one right now, if you've never seen it, is up here at ammonium phosphate, knowing that this outside 3 has to multiply in to give you 3 nitrogens and 12 hydrogens. All right. So here's something fun. What number of iron atoms and how many moles of iron are in 500 grams of iron? All right. So iron atoms is how many? Moles of iron is what? Well, okay, so I'm going to go to the periodic table. What are the things I know? Iron is 55.85 grams per mole. I know that I have 500 grams of iron, and I also know that Avogadro's number is 6.022 times 10 to the 23rd inverse moles. Now, I pulled Avogadro's number out because I see, okay, I've been given a mass of iron and I'm asked about number of atoms. Okay, that tells me I'm going to need to make a switch from mass to atomic based on moles because I know that I get grams per mole from the periodic table. So I'm going to have to filter out moles by using Avogadro's number. It'll become more automatic to see that as time goes on. All right. So let's do moles first because it's just a natural progression. Okay, so I'm going to start with what I have. I have 500 grams of iron, and I know that I can use the molar mass of iron to go from grams to moles or moles to grams. Okay, so I have 55.85 grams per mole. And you remember that's how that conversion factor works out. I need to put that in here in a way to get rid of grams. So some of you from high school, maybe you learned, well, I need to divide mass by the molar mass. Okay, same idea, same thing. So I need to put the 55.85 grams of iron on the bottom, leave moles on the top, and then grams of iron will divide out. And so 500 divided by 55.85 is going to be 8.953 moles of iron. Again, I do it in a way where I'm chasing units. So I have grams of iron in the numerator. So that means I need grams of iron in the denominator so those cancel out. And I'm trying to cancel out the units I don't want to get to the units that I do want, which is moles. And notice this was a division, but 500.0 and 55.85 are both four significant figures. So my answer has to be in four significant figures. Okay, so then let's go to, what was the next one? Atoms. Okay, so now I have moles, and I know that I can go from moles to atoms using Avogadro's number. And I know the Avogadro's number in this case, 6.022 times 10 to the 23rd atoms per 1 mole of iron atoms. And so when I multiply this up, I'm going to get 5.391 times 10 to the 24th atoms of iron. Because again, you see I have moles in the numerator, moles in the denominator, those divide out, and I'm left with the unit I'm after, atoms of iron. So here's one. What number of molecules are also known as formula units, are present in 1 gram of cal? So this one, you see the calcium ion. You see a polyatomic, that's phosphate, this is calcium phosphate. And then B, you see the sodium ion. Go back and make sure you're reviewing your naming of this one. So your PO4 is phosphate, HPO4, remember it's hydrogen phosphate. So this is sodium hydrogen phosphate. And again, their subscripts are putting these together in a way where their charges neutralize. You're going to get practice on that in your next assignment. Okay. Okay, what do I know? Calcium, 40.08 grams per mole. Phosphorus, 30.97 grams per mole. Oxygen, 16 grams per mole. And then Avogadro's number, all right. Yeah, I have one more thing that I could that I really know. I know I have 1 gram of calcium phosphate. All right. So that means I'm going to actually need the molar mass of calcium phosphate. Just going to do it. So we're going to need 3 calciums plus 2 phosphorus plus 8 oxygens. That's going to be 3, 40.08, 2, 30.97, 8 oxygens. And so calcium phosphate is going to come out to be 310.18 grams per mole. All right, now, so here's the thing. I want molecules. I can get number of molecules using Avogadro's number, but I have to get it to moles first because Avogadro's number will relate a certain number of molecules to a mole of calcium phosphate molecules. All right, so we can do this in multiple steps. So I can start by saying I have 1.0 grams calcium phosphate. I'm going to divide by the molar mass of calcium phosphate. So grams calcium phosphate, grams. And that's going to give me 0.00322 moles of calcium phosphate. And then I can take those moles and get number of molecules. Okay, so then 0.00322 moles. And this is where I use Avogadro's number. And so I know that I have 6.022, that's 10 to the 23rd molecules in 1 mole of calcium phosphate molecules. And so then, of course, moles and moles will cancel out. And when I multiply these together, I'm going to get 1.94 10 to the 21st molecules. All right. So let's look at part B. Part B, you notice we have sodium hydrogen phosphate. Okay, so I'm again being asked to find the number of molecules. And then I say, what do I know? I know that I have 1.0 grams sodium hydrogen phosphate. Sodium is going to be 22.99 grams per mole. Hydrogen, 1.01 grams per mole. Phosphorus, 30.97 grams per mole. And oxygen, 16 grams per mole. All right, so those are the things that I know. So then I can start in again. So I'm going to have to go from grams of sodium hydrogen phosphate to moles of sodium hydrogen phosphate and from moles to molecules. So I need the molar mass of sodium hydrogen phosphate. And so what am I going to have to add together? 2 sodiums plus hydrogen plus phosphorus plus 4 oxygens. That'll be 2, 22.99 plus hydrogen's 1.01 plus phosphorus 30.97 plus 4 oxygen 16.00. The mass of sodium hydrogen phosphate comes out to be 141.96 grams per mole. Okay, so now up here, I did my calculation in 1, 2 steps. You can break things down in as many steps as you want, or do it all as one big step. And so that's what I'm going to do now. I'm going to do everything as one big step. Okay, so I know that I have 1 gram. I know I have to get this into moles because I can't get number of molecules from Avogadro's number unless I have moles. Okay, so then I'm going to divide by the molar mass of sodium hydrogen phosphate, which is going to be 141.96 grams per mole. Okay, so now the units of grams have canceled out. I have moles, and I know that I have 6.022 10 to the 23rd molecules per 1 mole of sodium hydrogen phosphate molecules. And now moles has divided out. Go. And when I multiply this all up, I'm going to do multiply the top, divide by the bottom. This is going to give me 4.24 times 10 to the 21st molecules of sodium hydrogen phosphate. And again, I want to make sure you understand that name. So sodium comes from group 1 on the periodic table. So it has a charge of +1. So hydrogen phosphate, how do we get there? So phosphate has a charge of a -3. I'm going to add a hydrogen to make hydrogen phosphate. Since I added a hydrogen, it now has a -2. And so I'm going to make this neutral, I'm going to need 1 plus 1 minus 2. That's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2, that's neutral. Each one of these is a sodium. 1 plus 1 minus 2 There's my hydrogen phosphate, so I have to have two sodiums to the one hydrogen phosphate. And of course, its name just comes from the pair, the two ions that are paired together. So let's use this same idea to go a little bit deeper. What number of atoms of phosphorus are present in 1 gram of, again, we're going to use the calcium phosphate and the sodium hydrogen phosphate. Okay. A, atoms of phosphorus. Okay, so some things, what are things that I know? Again, calcium, 40.08, phosphorus, 30.97 grams per mole, oxygen, 16.0 grams per mole. Now, look at this formula. It's 3 calciums, 2 phosphorus, and 8 oxygen. So I have 2 phosphorus atoms per molecule. And that's the key to this one. Because we're doing what we did above, we're just taking it one step further. So Avogadro's number, because again, we start with the 1 gram. And you can write that down, not write that down. I'm not too worried about that. So again, we know we have 1 gram of this compound. So we need its molar mass, so we can turn it into moles. Avogadro's number, so we can turn it into molecules. Then you see we have 2 phosphorus atoms per molecule. So so let's do that. So and I'll put on your homework, problem by problem. I'm going to want to see you do this addition, figure out the molar mass of molecules until I'm sure you have the process down. Shouldn't take too long. So this is 3 calciums plus 2 phosphorus plus 8 oxygens. That's 3 times 40.08 plus 2, 30.97 plus 8 times 16. And again, you get the 310 grams per mole. Probably after this assignment, we'll just go to, so at least in this next assignment, I'm going to want to see you add these up. But then from there on, you can just give me the molar mass of the molecule and use it in your calculations. We won't have to do this every single assignment. I just want to make sure you have the process down. So again, we start with our 1 gram. Calcium phosphate. So I want to go grams to moles. So I'm going to divide by the molar mass. Grams per mole. Grams is going to cancel. Now I need molecules because I can only talk about atoms of phosphorus if I know the number of molecules. I have Avogadro's number of molecules per mole of molecules. So now moles divides out. And my last conversion factor is I have 2 atoms of phosphorus per molecule. The molecule unit will divide out. And so that leaves me with atoms of phosphorus. So I multiply 1 times Avogadro's number times 2. and divide it by 310.18. And I end up with 3.88 times 10 to the 21st phosphorus atoms. All righty. And so then part B, how many atoms of phosphorus in sodium hydrogen phosphate? Okay, so let's again do the things that I know. So I know for this molecule, I have one atom of phosphorus per molecule. I have my 1 gram, so sodium, 22.99 grams per mole. Hydrogen is 1.01 grams per mole. Phosphorus, 30.97 grams per mole. And oxygen, of course, is going to be our 16 grams per mole. What our Avogadro's number? So I have a list of things that I know to help me solve the problem. We need the molar mass, just because again, we're going to go from the 1 gram, use the molar mass to go to moles, from moles to molecules, and molecules to atoms. It can also help you solving problems if you make little maps like this. Like, what do I have and where do I have to go to? So if I start with a mass and I have to go to atoms, what steps do I have to go through to get there? Work on mapping that out. That can help you solve problems. So the mass of sodium hydrogen phosphate, you're going to need two sodiums plus hydrogen plus phosphorus plus 4 oxygens. That's going to be 2 times 22.99 plus hydrogen is 1.01 plus phosphorus at 30.97 plus 4, and your oxygens are 16.0. It's going to give you 141.96 grams per mole. All right, now I'm going to do my calculation again. I have my 1 gram sodium hydrogen phosphate. All right, so if I have a mass, I need to use the molar mass. I need to divide by it. 141.96 grams per mole. Going to get rid of grams. Okay, now I know that I have Avogadro's number. Molecules per mole of molecules. And then I know, so then of course, moles divides out. And I know that I have 1 atom of phosphorus per molecule. Okay, so then molecules will divide out. Now I'm going to multiply across the top, divide by the bottom, and I'm going to get 4.24 times 10 to the 21st atoms of phosphorus. All righty. So this is how you do calculations. using Avogadro's number, figuring out molar mass. We did average atomic mass. So that is going to bring us to an end for today. And we will continue on with chapter 3 next week. All righty. Thank you.